Hello and welcome to today's video. In this video, we're going to talk about a special kind of sequences that is called series. So this section is called series, and I'll give you the definition right away. So let's say you have a sequence AN or AK with index at n or n0. What we can then do is we can just sum up the elements of that sequence. And if we do that, we can define another sequence in that way. So we define these so-called partial sums, the nth partial sum for n in n0 as this partial sum is denoted by Sn, and it's defined as the sum of the AK starting from 0 to n. So this is the nth partial sum of the sequence AN. Now these partial sums define a sequence of their own, and that sequence is called a series with sums or elements AK. So the sequence Sn is then called a series with summons AK. Of course, we can also ask for such a sequence if it converges and what its limit might be. And if it converges, there is a special notation for that. So if that sequence Sn converges, then we say that the series is convergent or converges. So we say that the series is convergent. And we write it as the sum k from 0 to infinity. So we just denote the limit by adding an infinity here as the upper bound of AK. So that denotes the limit of the partial sum sequence Sn as n goes to infinity. So that is the notation for its limit. And of course, as usual, if the sequence is not convergent, then we call it divergent. Of course, there's also the case of a series that tend to plus or minus infinity, and we'll denote this in a similar way. So we write again this sum here from 0 to infinity over the AK, and we just say this is plus or minus infinity if the series diverges but tends to plus or minus infinity. And of course, there are also series that do neither, that diverge and do not tend to plus or minus infinity. We'll see examples of those. Two small remarks before we go on with examples. The first one is a series, as we have defined it, is of course a special kind of sequence. So all the results that we have derived for sequences also apply to series here. So that's The first remark is a series is a special kind of sequence all results for sequences carry over to the situation of series. And the second remark is, if we have a series that converges and look at the summons, at the sequence of summons, then this sequence of summons must also converge, and particularly it must converge to the limit of 0. If the summons are not converging, then of course the series itself will never reach a limit, because the difference of two subsequent partial sums must decrease if the series is going to converge. So if a series from a to infinity over a n converges, then the limit of a n is 0. Now let's have a look at a few examples. The first example that we will consider is called the geometric series. For that we need a factor q, so q is a factor in R, and the geometric series is then defined as the sum over the q to the power of k, where that power goes from 0 to infinity. And just for convenience, we'll assume 0 to the power of 0 is 1. So what that means is this series, this sum here from 0 to infinity over q to the power of k, that is 1 plus q squared, and so on. Now, what does that mean for the partial sums and for convergence of that series? So the nth partial sum Sn is then simply the sum from 0 to n of q to the power of k. And this is geometric sum. That's where the name geometric series comes from. So we have a formula for that. That means we can compute Sn. That is 1 minus q to the power of n plus 1 over 1 minus q. Now, of course, that only holds for q not equal to 1. If q is equal to 1, then what we're doing is we're summing up 1, 1, 1, 1, 1, 1, 1, and of course that will never converge. So we have handled that case already. For the others, if we look at this expression here, this 1 minus q is a constant. That doesn't change convergence. So the question is, what is this expression here doing? And basically, if that tends to 0, then of course we will have convergence. If that doesn't tend to 0, then we can't have convergence. So the result that we get is the geometric series from 0 to infinity over q to the power of k that either converges to 1 over 1 minus q, if that here goes to 0, and it does go to 0, if and only if that q is between -1 and 1, strictly between -1 and 1. So this is true for q's where the absolute value of q is strictly less than 1. It goes to infinity if q is greater or equal to 1, because in this case, as you can see here, this here will grow and grow and grow. So this will become a larger and larger negative number. Of course, this here is also a negative number, so it still goes to plus infinity then. Okay, so we have this here. On the other hand, if q is less or equal to 1, well, or -1, sorry, if q is less or equal to -1, what will happen is this is a positive number. This here is a number where the absolute value grows and grows and grows. But with the n plus 1 here, the sign changes. Yeah, so if you have an even number, then the sign is positive. If you have an odd number, then the sign is negative. And still with this minus sign here in front of it, the sign change is still there. So what happens is the number jumps around between positive and negative numbers, and their absolute values get higher and higher. So this series diverges, and it does not even tend to plus or minus infinity. So for q less or equal to -1, the series diverges. So that is a geometric series, one of the most important series that we'll encounter. Our next example will describe the so-called harmonic series. We've also seen series like that before. Let's first define that. So the series sum over 1 over k, that is called the harmonic series. And of course we have to start that at 1 instead of 0, because 1 over 0 is not defined. So this is called the harmonic series. Now, in other words, we write this out. The harmonic series is simply 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and so on. Let's go on to 1 over 8. And this continues indefinitely. Now, what can we know about convergence or divergence of that series? As you can see, the summands indeed do tend to 0, so that series might converge, but also note it doesn't have to. And indeed, what we can see here is we can group the summands here. So we can just take these two together. And as you can see, this is greater or equal to 2 times 1 over 4, that last summand here. And 2 times 1 over 4 is 1 over 2. Now this one here is also greater or equal to 1 over 2. And of course, so is 1. So we can do the next group, that is then 1 over 5 up to 1 over 8. So next we group 4 summands, and that is greater or equal to 4 times the last in that series is 1 over 8. So 4 times 1 over 8. And again, this is 1 over 2. So of course, the next group, where we then take not 4 but 8 summands, will also be greater or equal to 1 over 2. We can go on with that indefinitely. And that means what we get here is, this surely is greater than 1 over 2 plus 1 over 2 plus 1 over 2, and so on. So in the end, whatever number we set, we can go beyond that number by just taking enough of those groups that each have at least 1 over 2 as their magnitude. So what we get is this whole thing will diverge. We can surpass every number, and that means it tends to infinity. So the result here is the harmonic series diverges with sum from 1 to infinity, 1 over k equals infinity. So it tends to infinity. And note, the summands 1 over k, those will tend to 0. But the series still diverges. So for a convergent series, the summands have to tend to 0, but that is not sufficient for convergence. We can have series where the sequence of summands tends to 0, but the series itself is still not convergent. And this is an example for that. Now, finally, as our last example, let's consider the Euler series. This is related closely to the Euler sequence, and we'll see in a minute why this is the case. Let's first define the series. So the series k from 0 to infinity, 1 over k factorial is called Euler series. And why is it called Euler series? Well, the reason for that is it converges. And it converges with a limit that we all know, and that is Euler's number. So the limit of that series is Euler's number. And in the following, I'd like to prove that this is actually the case by making two arguments. To show that, what we do is we'll use the sandwich theorem. So what we have to do is we have to find two sequences that enclose this series from below and from above. And then we'll have to argue that both of these sequences converge to Euler's number. So the enclosed sequence, the sequence of partial sums of this series, also converges to Euler's number. The first point we're going to make is we're going to look at the limit of Euler's sequence. You know that is 1 plus 1 over n to the power of n. That converges to Euler's number E. And we're going to use a trick that we've used before. We're going to rewrite that using the generalized binomial formula. So this is the same thing as the limit of the sum from 0 to n of the binomial coefficients n over k times 1 to the power of n minus k times 1 over n to the power of k. So in effect what we get here is, again, that limit of the sum k from 0 to n of n times n minus 1 times n minus 2 and so on. That's the binomial coefficient that has k factors. So we need to go to n minus k plus 1. So this is k factors here. And then we have k factorial in the denominator. And we also have n to the power of k. That n over to the power of k comes from this one here. And the k factorial comes from the binomial coefficients. What we can do then is we can split this up and say, well, this is the limit of the sum here. And we just split up this n to assign one of these k's, one of the k n's to these coefficients here. So what we can do is we have this 1 over k factorial and then n over n times n minus 1 over n times n minus 2 over n, and so on, up to n minus k plus 1 over n. So one of these k factors here goes to each of these factors here. And we see that each of these is then less or equal to 1. And that means, of course, the whole thing is less or equal to the limit of this sum here of 1 over k factorial. And that's exactly the limit that we're interested in. So this is the limit of Euler's series. So that means if it converges, it will at least have a limit of e. It can't go lower. Now we have to also bound it from above. So this is our bound from below. Now we bound from above. And to that, let's say we have a number n in n0. We'll consider that one fixed. And then we only consider n's that are greater or equal to that capital N. It'll be apparent why we do this in just a minute. So what we're going to consider is, again, Euler's sequence, 1 plus 1 over n to the power of n. Again, as before, we can write that as a sum using the generalized binomial formula of the binomial coefficients n over k times 1 over n to the power of k. And what we do now is we cut off that sum at a certain point. So we're saying, well, our n, we assume that our n is greater or equal to capital N. So if we just cut off that sum at capital N here, then we know that our small n is greater or equal to capital N. So the left part has more summons, and all these summons are positive, or at least non-negative. So the right sum that we cut off is smaller or equal to the left sum. We're not going to do any more here. Again, we're going to apply the same trick that we did before. And that we mean we have 1 over k factorial times n over n times n minus 1 over n times n minus 2 over n, and so on, up to n minus k plus 1 over n. Yeah, you still remember that. And now we proceed differently. What we do now is we say, well, this is the sum from 0 to capital N over 1 over k factorial. And we will now take these sums here. We forget about that one, of course, that's just 1. And we write these as n minus 1 over n is the same as 1 minus 1 over n. Now, n minus 2 over n is the same as 1 minus 2 over n. And so on. So we can write it in this way. And the last one will then be 1 minus k minus 1 over n. So here we now have k minus 1 factors. Remember, we forgot about this 1 here. That was the kth factor. So this is k minus 1 factors. And we also know that k minus 1 is less or equal to capital N, because that is the upper bound here, right? For k. So what does that mean? Well, that means if we just replace all of these by by capital N, then of course that's the largest we can get, so that sum will get smaller, right? We're subtracting this expression here, so if we replace that 1 by a capital N, this will get smaller. If we replace 2 by capital N, this will get smaller, and so on. So we have this is greater or equal to the sum from 0 to capital N, 1 over k factorial. And now we have 1 minus capital N over N times 1 minus capital N over N, and so on. 1 minus capital N over N. Again, this is k minus 1 factors. And k minus 1 is less or equal to capital N. So we can say this is greater or equal to, from 0 to n, 1 over k factorial. And now remember, this small n is greater or equal to this capital N, so this factor is less or equal to 1. So here we have a number that is somewhere between 0 and 1. That means if you multiply more, then the whole thing will become smaller. And that means we can just say this is greater or equal to 1 minus n, capital N over n, to the power of capital N. Right? We have k minus 1s, k minus 1 factors here. K minus 1 is less or equal to capital N. So if we use capital N factors, that might be more, but that would only mean this product will become smaller. And now that's where we want it to be. Because we can now use this by saying, well, you remember that E is the limit of 1 plus 1 over n to the power of n as n goes to infinity. And this is surely greater or equal to, well, remember that's what we started with, right? This is the expression we started with. So this is greater or equal to this expression here. So this is greater or equal to, again, the limit as n goes to infinity of 1 minus n over n to the power of n, sum of 1 over k factorial, k from 0 to capital N. Right? And again, this is the limit that we're interested in. So we now know that E is greater or equal to that limit. Okay, remember this n here is going to infinity, the small one. The capital N is fixed. So what happens here is this here is growing. This is fixed. So this is going to 0. And that means this whole expression is going to 1. Right? So that's why that's not problematic. And that's why this bound actually works. So finally, we did it. By the sandwich theorem, we have shown that the series 1 over k factorial, k from 0 to infinity, is indeed equal to E by the sandwich theorem. So this concludes the last example for a series. In the following videos, we'll have a look at criteria for determining whether a series converges or not. That may make our lives a little easier in investigating convergence of series. And as usual, I hope I'll see you then.